Hey everybody, in this video we're going to talk about something known as a transmutation reaction, which can be used to model nuclear decay and lots of other nuclear changes as well. So let's get straight into it, starting with in the top right hand corner of the screen you'll see a little key that you can use to remind yourself of the symbols we use for different types of radiation like alpha particles, beta particles, gamma radiation. Even neutrons and protons can be thrown in as well, and there's lots of other versions of that, but those are just 5 of the most common symbols. Let's begin officially by describing what a transmutation equation is. It is a way to model. That means describe on paper, in this case, by writing down exactly how an unstable nucleus decays and other nuclear changes as well. We're going to take a look at how this works with an alpha decay. And we're going to do 2 versions. We're going to look at the actual nucleus itself, so obviously right here, and what you might see if you could see a nucleus undergoing an alpha decay. That means breaking apart and emitting or shooting out an alpha particle. Side by side to that, we're going to write what this transmutation equation would look like, so you can get the visual and the equation version. Following that, this video will include a bunch of examples to give you lots of practice writing these things. So let's start off with the first thing that would make up the transmutation equation, and that is you would need a symbol for this element before the decay takes place. So we're going to use isotopic notations for this. That means I'll count the protons first. Those are the blue positive ones, and there's 6 of them. Because there's 6 protons, I can go to a periodic table and look up. The 6 protons is going to be carbon. If I also count the neutrons, I think there's 8, 1, 2, 3, 4, 5, 6, 7, and 8 neutrons for a total mass of 14. So before the decay takes place, I have a carbon-14 atom. Now if you watch that nucleus, we're going to have it undergo the alpha decay at this point, which means a piece of it, the alpha particle, is going to break free and go flying off, and it essentially becomes a separate particle. In the equation, we represent that change with an arrow, and the arrow separates whatever was there before the nuclear change, and then after the arrow, we're going to write new isotopic notation symbols for whatever's there afterwards. As you can see, what used to have 6 protons now only has 4, and what used to have 8 neutrons is now only 1, 2, 3, 4, 5, 6 for a total mass of 10. One interesting thing about alpha decays and other decay processes is the types of elements actually change. So we started with the element carbon, but now that there's 4 protons, it is a completely different element altogether. In this case, Be, beryllium, with a mass of 10. Beryllium-10 is not the only thing that we produced, of course. We also produced the alpha particle itself, which its symbol again is He24, and that's this little chunk that would have gone flying off into the universe. Technically, this alpha particle has a +2 charge. You can include that or not. It just sort of depends on your teacher's preference. And that equation is a transmutation equation. One thing to note about these is the atomic numbers and the atomic masses on opposite sides of that arrow will always equal one another. If I go back so we can see that, I'll highlight it in a different color. This is very helpful when it comes to writing these things yourself. What it means is, before the change, I had a total of 6 protons, and after the change, I had that exact same 6 proton total. This will always be true in any of the changes you see, and it works with the masses as well. Before, we had a total mass of 14, and after the change, we also had a total mass of 14. So those totals will always be equal to each other on opposite sides of the arrow. So I'm going to go through 2 more examples now, another alpha decay so you can see it start to finish a little bit faster, and then we'll do a different decay, a beta decay following this. We're going to do here the alpha decay of nickel 60. So again, the first step is to write the isotopic notation for nickel 60. That's nickel with a mass of 60. You would need to go to a periodic table and look up the atomic number of nickel. So on one that I've got, I can see that nickel's atomic number is 28. Since it's decaying, that means I'm going to write the arrow. Now it's breaking apart. One of the things that it's going to produce is the alpha particle He24. And now I have to predict what is left behind after that alpha particle leaves. Remember, if I start with 28 protons, before the change, I need to end with a total of 28 protons after the change, which means this new particle has only 26, because 26 plus 2 is the 28 that I started with. Same thing with the masses. If I started with 60, my new particle has to have a mass of 56 to combine with that 4 to get 60. If you look up what element has an atomic number of 26, you would see that it's Fe, iron. So here's my alpha decay for nickel 60. In this next example, we're going to do the same thing, but now for a beta decay of potassium 40. It begins the same way. Write the isotopic notation for potassium 40. My periodic table tells me that it has an atomic number of 19. The arrow following the arrow will put the symbol for a beta particle, which is -1, 0. Now this is a little bit strange. If you just trust the math, it'll work out, but conceptually it seems weird. We start with a total of 19 protons, and afterwards we have to have that same number, that same 19. However, because a beta particle has -1 in for the atomic number, the correct value there is 20. 20 plus -1 gives me that 19 that I started with. I'm going to switch back colors now to fill out what element that is. I think it's calcium. The masses are pretty simple. Potassium has a mass of 40. The beta particle doesn't have any mass, so my calcium has all 40 of those mass units. So on a mathematical sense, or in a mathematical sense, that is fine, right? 20 plus -1 is 19, which is the number I started with. Conceptually, though, that's kind of weird, because we're saying that potassium had 19 protons, and then somehow we have gained a proton. Calcium magically has 20 protons. And the answer is that's how beta decay works. I think officially what's happening is, during the beta decay process, a neutron is literally converting into a proton. And as that happens, an electron is released as a byproduct. That electron becomes the beta particle, and we have gained a proton in the process. You don't really need to know that, I just throw it in as an explanation behind how this can even happen. Here's 2 more examples. Ideally, you would pause the video and try these yourself before watching me go over the answers, assuming you've had a chance to try that, or if you just want to follow along, here we go. We'll start with the symbol for arsenic 80. Its atomic number is 33. Get that from a periodic table. Its mass is 80. If it undergoes an alpha decay, then it emits the alpha particle, leaving behind 31 protons and a mass of 76. 31 protons tells me that I now have an atom of gallium. If cobalt 60 undergoes a beta decay, we'll start with the symbol for cobalt 60. I believe cobalt has 27 protons. This atom will decay, emitting this time a beta particle, which weirdly enough means my new atom has 28 protons. 28 plus -1 gives me that 27 that I started with. The mass is still 60, and since it's now got 28 protons, we are back to an atom of. So that wraps it up for this lesson on transmutation equations.